Hello everyone and welcome back to the channel. So this video is going to be part of a new playlist on binary search, and in this series we will be discussing the concept of binary search and also some practice problems to consolidate our understanding of the concept. As usual, the expectation would be that after watching this playlist you should go online and search practice problems on binary search and try to write the code by yourself and submit it. And I can assure you that if you follow these two steps, you'll be able to solve most of the problems on binary search. So without any further ado, let's get started. And this video will concentrate on the concept and basic code for binary search. We will also discuss the constraints, the prerequisites, and the time complexity for binary search in detail. And as usual, all the timestamps will be there in the description. So search in general means that you're given a search space or a collection of elements, and then you're given a target and you need to find this target in this search space. So the return type is generally a boolean true or false depending on whether you were able to find the element or the target, or you need to return the position of the target in this search space. This is very generic, and let's get more specific and assume that the search space is an array of integers and target is also an integer. Once we are clear how it works for an array, we will be able to expand it for other data containers like matrices and stuff. So given an array, let's take an example. We are given an array 4 comma 1 comma 8 comma 6 comma 7, and the target given to us is 7. We need to find 7 in this array, and what we need to do is we need to return its index in the array, and if it is not present in the array, we need to return -1. A very naive approach would be to parse the array once, and during the traversal we compare each element with the target. If it is equal, we return the index, otherwise we return -1 once we are done with this parsing loop. So this is a very valid approach actually, and it is known as linear search. And the time complexity for this approach is actually big O of n. So why is the time complexity big O of n? Because we know that there are n elements in the array and we are traversing the array completely once, and to traverse the array we would have to check each element, and since there are n elements, the time complexity will be big O of n. Now binary search is an enhancement over the linear search and has a much more efficient and optimized complexity. So let's see how it works. Just one prerequisite: for binary search to work, the array needs to be sorted in increasing or decreasing order. So let's assume this to be true. I will explain the reason in few minutes, but let's assume that this is a prerequisite for binary search. So let's take another example array and understand binary search using this array. So we are given an array 1 comma 5 comma 17 comma 45 comma 88 comma 101 comma 120, and let's assume that the target that we are trying to find out is actually 101. So we need to find out 101 in our example array. So what we can see that this array is already sorted in increasing order, so or non-decreasing order, because the elements can be equal to the previous element. So rather than increasing or decreasing, we can say that it is sorted in non-increasing or non-decreasing order. So this particular array is sorted in non-decreasing order. So let's say if I pick any element randomly from this array, say I pick 17. So I have 17 here and I have picked 17, and I try to compare 101 and 17. I know that my target 101 is actually greater than 17, right? So 101 is greater than 17. And also we know that the array is sorted. So is there any possibility of finding 101 on the left side of 17? Obviously no, because 101 is greater than 17 and all the elements which are greater than 17 or equal to 17 are going to lie on the right side of 17. So obviously there is no possibility that I will find 101 on the left side of 17. So after this one comparison, I can easily discard the entire left side, which in this case contains 1 and 5, right? So the entire left side can be discarded. Now, if you try to analyze this particular step and try to understand this step, we see that in our linear approach, we were discarding only one element after every comparison, and this one element was actually the current element. So we were only discarding the element with which we were comparing the target. But here, after every comparison, we are discarding one or more elements as one. So now you can sense the power of binary search. So now the element that we pick for comparison, which was 17 in the above case, is actually called a pivot element. And in binary search, the pivot element is always the middle element of the remaining array instead of a random element. So as you saw, that 17 we picked up randomly and did a comparison and then discarded the left side. But for the case of binary search, the pivot element that we are going to pick is always going to be the middle element of the remaining array. So if pivot element is always the middle element of the remaining array, we will essentially discard half of the remaining array every time. So does that make sense? Yes, actually it does. So if we have a remaining array and we have picked the middle element, and after every comparison we either discard the entire right side of the pivot or we discard the entire left side of the pivot. Now if you have the middle element and you're discarding the left or the right, you're essentially discarding half of the elements of the remaining array every time. And that is why binary search is so strong, because in linear search we were discarding just one element. In binary search, at every step we are discarding half of the elements. So let's try to dry run this approach on the above example with a different target. So let's take the example as 1 comma 5 comma 17 comma 45 comma 88 comma 101 comma 120, and the target that we are trying to find is 88. Now the middle element in this case is 45 and we compare 88 and 45. Obviously 88 is greater than 45. Since 88 is greater and elements are in increasing order, we can discard the left side of 45, because we know that 80, since it's a sorted array, 88 is always going to lie on the right side, so there's no need to do a binary search on the left side of 45. So at this particular scenario, we discard the entire left side, and we also discard the pivot element, like because we know that 88 is obviously not equal to 45, so keeping pivot element also would not make sense. So when we are discarding the right or left, if we discard the pivot element as well along with that, it would not make any difference. So now the remaining array that we have once we have discarded our elements is 88, 101 and 120. Now again the middle element is going to be 101. We do a comparison and we know that 101 is greater than 88. Now since my pivot element is greater than my target, I know that I am not going to find the target on the right side of this pivot element. Obviously this target is going to exist on the left side since it's sorted. So again I can discard the pivot along with the right side. So my remaining array is 88. Obviously the middle element is 88 and what I was trying to find was also 88. So my pivot is equal to my target. So now I can return the answer from here, and the answer would be the index for this particular remaining element. So using binary search, we have actually found our answer. Now let's consider if this element, the remaining element, would have not been 88, but let's assume that a remaining element would have been 87. There was no 88 in our original array. The element which was 88 was actually 87. And in this particular case, the element which would have been picked as the pivot would have been 87. And we would have seen that 87 is again not equal to 88 and 87 is less than 88. So obviously we discard the pivot element as well as left hand side. So there's no left here. So we'll discard the pivot element and the remaining array would be an empty array. So actually when the remaining array is an empty array, that tells us that we need to stop our binary search, and the element which we are trying to find, or the target which we are trying to find, does not exist in the array. So from here we return -1. One more thing to add here is that we saw that always our remaining array was odd, and it was really easy to pick the middle element because it's really clear that in an odd size array the middle element would be n plus 1 if the size of the array is n, say 7. So the middle element is always going to be the n plus 1 by 2 element. So in this case, the fourth, if the size is 7, the fourth element is going to be the middle element. But in the case when the size is even, you might think that what would be the middle element. So it actually does not make any difference that which element you pick as the middle element. So if the size of the array is 8, then there are two candidates for middle element. You can pick 4, you can pick 5. So it actually does not make any difference which element you pick. So you can either do a ceil or you can do a floor, and you can pick any element as the middle element and just continue with your binary search. So let's quickly try to analyze the time complexity of binary search. So if I have n elements in my initial array, so let's assume that this is the initial array and I have n elements. So what I do is that I pick a pivot. So that is a constant time operation, O1 operation. And then I do a comparison between the pivot and target. Again, that comparison is a O1 operation. And after this O1 operation, my remaining array will have size n by 2, because I would have discarded half the array. Now again there would be O of 1 operations, again picking the pivot and then comparison, and after that again my array would, half of the array would have been discarded and my array would be n by 4. So if I continue this, what is going to be the last case? The last case would be when the size of the array is 1. So this is the last time I am going to do a O1 operation. After that my size will be 0, and if I have not found the element till now, then obviously the element does not exist in the array and I can return -1. So now we see that at each step we are doing a constant operation, and the time complexity will be equal to the total number of constant operations that we have done. And so the total number of operations is obviously going to be equal to the total number of steps in this tree. So how to calculate the steps in this tree? We know that at every time the size of the array gets divided by 2. So how many total steps do we need for going from n to 1? By constantly dividing it by 2. So we know that the total number of steps in this tree are basically going to be log n to the base 2. So these are going to be the total number of steps for reducing n to 1 if we constantly keep dividing it by 2. So the total operations, or the final time complexity that we have for this solution or binary search is going to be big O of log of n, because that is the total number of operations we are going to do in the worst case scenario, when the element does not exist in the array. So just going back to the recursion series, we can also view it recursively, and it will be just a good revision or a exercise to view this recursively. So I assume that at a particular step, my job is just to compare the target and the pivot element. And if the pivot element or target is equal, I'll just return the answer. If it's not equal, I'll delegate the same task to my recursive method for the remaining half of the array. So either the left half or the right half. So I don't have to worry how my recursive method works for the right half or the left half. I just assume that it actually works. And assuming that, I just need to do my job at the current step, which is comparing the current pivot and target. By using our recursion intuition, we'll be able to solve this problem. And actually we can show this binary search, or we can write this binary search as a recurrence relation very easily. So if we assume that f of n is my binary search on the complete array of size n, and then at each step what I do is I do a constant operation, and I assign the remaining task to the same relation, to the same function, and but for the remaining half of the array. It could be the left half, it could be the right half. So we know that when we solve this recurrence relation, it again comes out to be log n to the base 2. So using this recurrence relation as well, we can prove that the time complexity is going to be log n. But yeah, I think intuition and the tree approach for proving the time complexity is much better than this. Now you might say that the time complexity of this approach might be better, but the prerequisite is sorting, and that itself would take n log n time, which is greater than O of n for linear search, for the complete linear search. So if we are doing sorting, if we are given an unsorted array, then the total time complexity would be n log n for sorting plus log n for binary search. So the total complexity would be n log n, which is greater than linear search. So how does it make sense to do binary search all the time? Why is binary search better? That is true, but assume a case where the array is already sorted. Binary search is a much efficient algorithm than linear search in that case, or a case where you need to search more than once. So let's assume that we need to search queue time, that is, we are getting queue queries, and for each query we need to do a search, and the order of queue is approximately equal to the order of n. Now for linear search, it would take big O of q into n time, right? Because for every query, you would have to do a linear search. For every query, the linear search would take big O of n time. So the total time complexity would be the total number of queries into n. So the time complexity turns out to be big O of q into n. But binary search will take big O of n log n time for sorting. So for binary search, you first sort the array, which takes big O of n log n time. And this sorting step is a one-time step. You do not need to repeat this sorting for each query. Once you have sorted the array, you are done. So n log n time for sorting. And then for each query, you will run a binary search. So each query will take log n time for binary search. So the total time complexity would be q of log n. So now you see that you have completed your task in big O of n log n plus big O of q log n. And since we know that the order of n and q is approximately equal, we can say that the final time complexity would be q log n. Now assume that n is equal to 10 raised to power 5 and q is also equal to 10 raised to power 5. You will see that linear search would not even work. So q into n would not even work. And binary search, which is big O of q log n, would work in this case. So we see that binary search is actually powerful in cases even when the initial or the given input is not sorted. Now, as we saw for numbers, this approach can be applied for any container where the elements are monotonic, meaning the elements are following a certain trend in a particular direction. So, and just remember monotonic and not strictly monotonic. Because if I am at an element, the element can be greater than equal to or less than equal to its previous element. So the elements can be in non-decreasing or non-increasing order. It does not have to be strictly increasing or strictly decreasing order. And this is actually very similar concept to your monotonic functions. So in our above example, the monotonic property is that the magnitude of a number is greater or equal to the number on left. So it can be anything else. In a array of string, the string on right always has greater number of vowels than the string on left. So the trend being followed is that the number of vowels in each string is increasing as we are moving. And like this, the input just need to follow a trend in particular direction. Because without this trend, see what this trend is ensuring is that we are discarding the left and the right side. Because of this trend, we know that this particular element cannot exist on the right or the left. If this trend is not followed, or without this trend, we won't be able to discard a part of the array, because an element which is smaller might be on right or might be on left of the pivot. This monotonic property was ensuring that the smaller element will always be on the left. So that's why this particular trend in particular direction needs to be followed. So now that we have discussed the concept, let's quickly understand the basic code for binary search. Binary search can actually be done iteratively or recursively, as we have already discussed. Since we are able to write the recurrence relation, obviously there exists a recursive solution. I will write the iterative approach because that is most widely used, and that is, I think, a more optimized approach. But writing recursive approach is also very important because the intuition comes in very handy while understanding other algorithms or concepts like merge sort. So I will write the iterative solution here. What you guys can do is try to write the recursive solution on your own. You can write it in any online ID like ID1 or anything, and you can post, if you want, you can post your solution in the comment section. I'll try to open each link and try to analyze your code. If I have any comments, I'll let you know in the reply section. But in just in case, if you want to practice, that would be a great way to practice. So let's quickly write down the code for binary search. So this is the main prototype of our method for binary search. So it simply returns an integer which is the index of the element, and if we are not able to find that element in the array, we return -1, and the vector is the collection or the array that we have, and the target is the number we are trying to find. So again, when we start, obviously we are considering the entire array. The remaining array is actually the entire array, and every time we'll be representing the remaining array with 2 pointers, which will be at the extreme end. So the start of the array will be represented by I, and the end of the remaining array will be represented by j. So right now the remaining array is the complete array. So I is initialized as 0, and j will be initialized as num dot size -1. So our binary search, as we know that since I is representing the start of the remaining array and j is representing the end of the remaining array, so when I is equal to j, we have an array which is of size 1. If I and j cross each other, so that obviously means that the size of the remaining array is 0. Because I and j have crossed each other, the start of the array is actually greater than the end of the array, which is not a valid case. So and we know, we have already discussed that we'll break the loop when the remaining array is of size 0, because we have seen the entire array, and we know, we have actually not seen the entire array, we have analyzed the entire array, we know that the target is not there in the array, so we'll return -1. So while I is less than equal to j, we'll find the mid index, which is going to be the index of the pivot, and then we'll try to compare this middle element with our target. So there are going to be three conditions. First is that the pivot element is actually equal to the target. The second obvious condition would be that mid is greater than the target. Obviously the third condition will be that my pivot is less than the target, and here we end the while loop. So in the case when my pivot element is equal to target, I have definitely found an answer, and we can simply return this index from here. So I will return the index which is mid. So now my second case is that my pivot element is greater than the target. So let's see what should we do here. If my pivot element is actually greater than the target, one thing I know that is the target is obviously going to be on the left side of my current pivot. So what I know is that I can discard the entire right hand side of the pivot along with the pivot. So to discard, what we need to do, let's see with a quick example. So if this is the array and I is here and j is here, and say pivot is 3, or let's assume that pivot is 4 and we are trying to find 3. So pivot is at 4 and we are trying to find 3, and we know that 3 is less than 4. So what I can do is I can obviously discard the entire right side of the pivot, which is 5, along with pivot. Now to discard this entire array, what is the obvious step I need to do? I just need to move j behind the middle element or behind the pivot element. If I have moved j to an element which is just behind the middle element, I have discarded the entire right side along with the pivot element. So that is the exact thing that we are going to do here. So what we are going to do is that we are going to move j to mid -1. Now by very similar logic, in the other situation we have to discard the left side of the array along with the pivot. So the very obvious step is to move I to mid +1, and this is the entire, and obviously let's return -1 outside the loop in the case where we have not find the answer, and close our function. So this is the entire logic and entire code of binary search. you'll be replicating this code a lot of places. So most of the problems will use binary search as a helper function, or will be a binary search will be a part of the problem. Like you would not get that write the code for binary search most probably, and it will be part of some problem or a bigger use case. So this method you will be writing a lot of times as a helper method to support binary search. So this is the entire logic of binary search. So yeah, I guess that's it for the main introduction and concept of binary search. Just in case if you still have any doubts or you did not understand anything, do mention in the comment section and I'll try to resolve your queries. And see you in the next video. Till then, take care and keep learning. Bye bye.